Bismillahirrahmanirrahim. Hello students, welcome to my YouTube channel Electrical Engineering. In today's lecture, I am going to start a lecture series on DC machines. In DC machines, the main contents of the course are magnetic circuits, transformers, DC generators, and DC motors. The recommended books for this course are Electrical Machinery Fundamentals, written by Stephen J. Chapman. The second book is a textbook of electrical technology written by B.L. Thiraja and A.K. Thiraja. In the first part, I will demonstrate the introduction of magnetic circuits, the underlying laws of physics, and some example problems in which I will show you how to solve a magnetic circuit. So the discussion on magnetic circuits is based on the Ampere's law. Ampere's law is defined as the line integral of magnetic flux density around a closed path is equal to the current enclosed. The definition of the Ampere's law can be explained by using this current carrying conductor, which is a straight wire, and if we integrate the closed path around this current carrying conductor uh, using B dot dl closed integral, that will be equal to mu I, and here mu is the permeability of the medium, I is the current enclosed by this closed path. So if the closed path considered is the circular path, then this integral will be equal to b into 2 pi r, and 2 pi r is the circumference of this circle. But any arbitrary closed path can be considered, for example square, rectangular, or any polygon shape can be considered, but in that case the solution of this integration will be different. So piecewise integration has to be considered in that case. So mu is the permeability of this medium which is surrounding this current carrying conductor, and B is the magnetic flux density, and 2 pi r is the length of the closed path. And we know that B is equal to mu H. Here H is the magnetic field intensity. If we substitute this expression over here, we will get H is equal to I over LC. And if we have a coil which has n turns, then this expression will be multiplied by n, because for more number of turns, the magnetic field intensity will be higher. So there is a direct relationship of the magnetic field intensity with the number of turns of the coil. But for a straight wire which is carrying current, the number of turns are considered to be 1. So now we have to calculate the length of this closed path from which the flux is flowing. In this case, the flux is flowing through the air. So if we want maximum flux interaction or maximum propagation of the flux through the closed path, we have to consider a ferromagnetic material whose permeability is very high. So we can consider this rectangular core which is made up of a ferromagnetic material, and now in this case we have to calculate the length of this closed path. Now the length of the closed path will be different at around the cross section of this core. So mean path length will be considered every time, and mean path length will be actually the length of this dashed line, which is actually length calculated at the mid of each segment of this core. Okay, so these are the turns which have been designed at this leg, and this flux phi is flowing through this closed core, and current I is made to flow through this coil, and magnetomotive force is equal to n times the current. N are the number of turns. So this is called magnetomotive force, and the flux is flowing through this core, and the core has the length LC. Now this circuit has the direct analogy with a typical electrical circuit, which is drawn here. V is the electromotive force, current I is flowing through the circuit, and R is the resistance. Similarly, in this circuit, F is the magnetomotive force, flux phi is flowing through this closed core, and R is the reluctance of the core. So reluctance is the analogous quantity to the resistance, and the reluctance can be defined as the opposition offered to the flow of magnetic flux. And Magnetomotive force is equal to flux times reluctance in the similar way as voltage is equal to current times the resistance, and also magnetomotive force is equal to number of turns times the current. So the reciprocal of the reluctance is called permeance, and there can be several reluctances connected either in series or parallel. In that case, in this, the equivalent reluctance for series connection will be the algebraic sum of all the reluctances, and in the parallel case, the reciprocal of the reluctance will be equal to the reciprocal of individual reluctances connected in parallel. And flux is equal to B into A, which is the product of magnetic flux density times the area of the cross section of the core, and this can be expanded using mu and I divided by core length multiplied by area, and we can rearrange this expression as this one, and Ni is the magnetomotive force, and mu A over Lc. Now this term is equal to 1 over reluctance. For example, I is equal to V over R. Similarly, in this case, flux is equal to magnetomotive force divided by the reluctance. And this is actually 1 over R, so reluctance will be equal to Lc over mu A. Again, another term which is associated with the magnetic circuits is the leakage flux, which is actually the flux leaving through the highly permeable core into low permeable air. And the relative permeability of air is equal to 1, and relative permeability of other ferromagnetic materials varies from 2000 to 6000. So greater is the relative permeability, smaller will be the reluctance. And when the reluctance is small, the flux will be maximum. So that was all about the introduction of the quantities which will be involved in solving magnetic circuits. And now I will move towards solving some example problems in which I will show you how to solve a typical magnetic circuit. So this is a simplest form of a magnetic circuit in which we have a binding at this left leg, and this is a closed core through which flux phi is flowing, and the dimensions of this core are specified over here: 15 centimeters, 30 centimeters, and 10 centimeters. Similarly, the top leg has 15 centimeter width. This length is actually 30 centimeters, and this lower leg has 15 centimeter width. So all these three legs have identical dimensions, but this right leg has smaller width. So this leg is actually narrow, so we have to calculate the path length of each leg, and the reluctance offered by these three legs will be identical, and the reluctance offered by this right leg will be small. So number of turns are equal to 200, and mu r is a relative permeability which is 2500. Current I is equal to 1 ampere, which is made to flow through this winding. And now we can calculate the area of this right leg. The depth of this core is equal to 10 centimeter, and area will be equal to width multiplied by the depth. So for this leg, width is equal to 10 centimeters, and depth is also equal to 10 centimeters. So area of this leg is equal to 100 centimeter square, or 0.01 meter square. Similarly, the width of these legs is 15 centimeters, so their area will be 0.015 meter square. Now we will calculate the reluctance of this right leg, which is given by this expression, and we will substitute all the quantities in this expression, and this turns out to be 14,300 ampere turns per Weber. Similarly, the reluctance of these three legs will be identical, and just we have to calculate the length of these total length of these three legs, starting from this point to this and this. So this total length is calculated to be 1.3 meters, and after substituting all these values in this expression, the overall the reluctance R2 will be calculated as 27,600 ampere turns per Weber. Now the equivalent reluctance will be equal to R1 plus R2, and this will be equal to 41,900 ampere turns per meter. Since same flux is flowing through all these four legs, so it will be considered that all four legs are connected in series, so their reluctances will be added. Now we will calculate the MMF, which is number of turns time current. So it is 200 ampere turns, and the total flux can be calculated as mmf divided by the reluctance. This is equal to 0.0048 Webers. This was the objective of this problem, to calculate the flux throwing this closed core. So that was all about this first lecture on magnetic circuits. I hope you have enjoyed and learned basic things related to magnetic circuits. So for watching more similar videos, stay tuned to my YouTube channel. Until the next lecture, it's goodbye.